The eighth continent they hid from you. Why Zealandia proves Earth is breaking. The ship's sonar lit up with a plateau the size of a country. That can't be right, someone said, staring at a ridge that shouldn't exist. A hidden landmass, thick crust, broad shelves, rose and fell beneath waves like it was breathing. If it's moving, coastlines, quakes, and resource maps are wrong. Your risk zones are wrong. Scientists mapped it. Government shrugged. Oil companies quietly listened. And here's the part nobody likes. This isn't a myth. It's Zealandia, a continent mostly underwater, reappearing in the data. The question isn't if it's real, it's why it stayed invisible, and what its restlessness says about Earth now. We're not doing a lecture. We're following a trail of clues that starts with Cold War sonar and ends with a test that might upend how we plan for the next 50 years. This unfolds like a detective story. First, the ocean whispers, bathymetry and satellite gravity tracing a ghost outline. Then the rocks speak, zircons, granites, and a crust thicker and slower than the surrounding seafloor. Next, we watch a continent drown in slow motion, rift by rift, plate by plate, until 90+% slips below sea level. Meanwhile, a different battle plays out on the surface. Names, budgets, maps, and whether continent is a scientific label or a political key. 3 payoffs you'll get. What Zealandia actually is, why it stayed hidden in plain sight, and what its movement predicts about the near future along the Pacific Rim. We'll track the Alpine Fault and the subduction arcs that tug at Zealandia's edges. We'll listen to drowned forests and stranded beaches. We'll pull climate time from cores and see whether uplift pulses and mantle anomalies are pushing this continent up and down like a slow tide. One detail, easily overlooked, flips the ending. It's a measurement that keeps refusing to line up with the tidy map. We'll plant it now and test it later. If it holds, it means our timelines for hazards and planning are too slow. To understand how a continent can vanish without an asteroid or a myth, we go back to when the ocean started talking, and the first outlines of a lost world flickered into view. The ocean started talking, sonar, satellites, and a ghost outline. The first clues weren't on a chalkboard, they were in the noise. Mid-20th century sonar built to listen for submarines kept bouncing off a shallow rise east of Australia. The returns looked like a shelf, not a ridge. Too broad, too smooth for typical oceanic crust. Mariners called them banks and plateaus. Geophysicists took notes and moved on. Meanwhile, gravity satellites began to sketch the sea surface like a fingerprint analyst, reading tiny bumps caused by mass below. The pattern came back. A vast high draped in sediment, wrapping around New Zealand, continuing toward New Caledonia. It didn't look like scattered scraps. It looked like a continent's shoulder submerged. Here's why that matters. Oceanic crust is thin, dark basalt, fast, dense, and born at ridges. Continental crust is thicker, buoyant, silica-rich, granite and its cousins, slow to sound waves, higher to float. Bathymetric maps and satellite gravity kept pointing to something elevated compared to abyssal plains, with the kind of subtle roughness you see where a continent's broad shelf drops to deep ocean. It was too large to be a microplate, too coherent to be random fragments. The cartographic outline, if you dared to color it, wrapped a region about 4.9 million square kilometers. That's India-sized. Rocks do. But outlines don't settle arguments. On a research vessel in choppy seas, a crew stared at real-time readouts showing crustal thickness, numbers creeping higher than typical ocean floor. Someone muttered, "That's continental?" It was a double-take moment. Another survey crossed a ridge where seismic waves slowed, the way they do in lower-density crust. The instruments weren't drawing a fantasy. They were reading buoyancy. While that was happening offshore, satellite altimetry made the ghost brighter. Sea level isn't flat. Water piles slightly over dense masses and dips over gaps. Convert those tiny tilts to gravity anomalies, and you get a quilt of hidden mountains and basins. Across the Southwest Pacific, the quilt stitched a single fabric, split by rifts but continuous in character. New Zealand and New Caledonia weren't lonely travelers. They were the highlands of a drowned plateau. What nobody knew at the time was how much this classification would matter. If this was a continent, it would reframe hazard models, exploration rights, and scientific priorities. If it wasn't, it could be dismissed as marketing. In labs and conferences, the debate sharpened. Was this an oversized volcanic province, thick lava over old floor, or genuine continental crust thinned by ancient rifting? Large igneous provinces can be broad and high too. The difference sits in composition, thickness, and behavior under seismic waves. So marine crews kept crisscrossing the suspected edges. They mapped continental slopes where depths dropped from 2 or 3 kilometers to 4 and 5, marking the base of a shelf-like margin. They traced sediment drapes with reflectors that screamed continental erosion, not mid-ocean ridge birth. They towed magnetometers that didn't sing the tidy striping of youthful ocean floor, and they drilled. When cores came up, the sediments told a familiar story. River-delivered grains, shallow marine fossils, and sequences that looked like the drowning of a shelf, not the slow dusting of abyss. 3 days earlier, a different team had puzzled over a satellite gravity swath. A long, linear low where a trench would be if subduction had once hooked in and pulled. Across town, a modeler tried stitching in known fracture zones and came up short. The pattern only made sense if a broad area had continental density from the start. The more lines they added, the cleaner the silhouette became. It wasn't perfect. Zealandia was rifted, faulted, stretched thin in places. But so are continents that have been pulled apart. Get this? They actually tried to ignore the outline for a while, because a contour line isn't a continent. You need crustal velocities and compositions. You need zircons, those tiny timekeepers that carry the age of continental roots. You need seismic refraction that marks a moho deeper than oceanic norms. Bathymetry and gravity are the whisper. Geology is the testimony. Still, the whisper had done its job. It had told the ships where to look, and the labs what to test. It had shown that 94% underwater doesn't mean imaginary. It just means hidden by habit and instrumentation limits. The ghost outline forced a better question. If the seafloor can hide a continent this big, what else sits beneath our certainty? Meanwhile, in the wheelhouse, a tech fixed a glitchy display while the ship rolled. The latest line of sounding showed the slope steepening, base of the shelf ahead. The chief scientist walked in, coffee sloshing, and traced the contour with a finger. There, they said. If it's real, the crust changes here. The crew nodded, set the instruments, and aimed for the break. But a pretty map doesn't write a new chapter. Rocks decide. The next step would leave the screens and enter the cores, the crystals, and the slow waves that pass through Earth like a lie detector. And that's where the case for Zealandia would either crumble or lock into place. Rocks don't lie. Continental crust where it shouldn't be. Maps pointed the ships, but the verdict would come from minerals that don't care about hype. In a lab that smelled faintly of acetone and wet rock, a technician labeled a bag of sand-sized crystals and fed them into a laser ablation setup. Tiny zircons, clear, stubborn timekeepers, flashed. The dates came back old. Not young, mid-ocean ridge young. Gondwana old. Hundreds of millions of years, 300+ million in places, with age spectra matching continental basement, not oceanic veneer. Get this. The first readout looked so wrong the lab notebook got an asterisk. Check label? The label was fine. The map was wrong. Continental fingerprints were hiding beneath blue water. Here's why zircons matter. They're tough, they lock in uranium lead clocks, and they don't form in typical oceanic basalt. You find them in granites and continental volcanic arcs. When they show up in sediments draped across a plateau, they tell you the source rocks had continental roots. Meanwhile, whole rock chemistry from dredged samples leans silica-rich. More granite, more rhyolite, fewer basaltic thuds. It wasn't just one weird pebble, it was a chorus. While that story built grain by grain, seismic crews drew cross-sections with sound. Refraction and reflection lines lit up a crust that was thicker and slower than oceanic norms. Oceanic crust is usually around 6 or 7 kilometers thick. Across broad swaths of this plateau, velocities and conversions put the moho much deeper. 20, even 30 kilometers in places, thinning where rifts had pulled it like taffy, but still firmly in the continental camp. Low seismic velocities in the upper crust fit felsic rocks. The waves took their time, like they do through buoyant continental material. Aboard one survey, a graduate student watched first arrivals on a monitor step out later than expected. The supervisor leaned over and did the mental math. That's not basalt, they said. Not in that much volume. Unknown to them, across town, a modeling team fed those velocities into a crustal thickness inversion. The output map showed blobs of deep crust merging into a nearly continuous swath from north of New Zealand to New Caledonia. Broken by basins, sure, but stitched by continental properties. Then came the granite signatures. Isotope ratios, strontium, neodymium, carried the memory of crustal recycling. Oceanic plates don't tell that story. Continental terranes do. And when they measured densities, the numbers lined up with a piece of crust that wanted to float higher than abyssal plains, which explained the persistent bathymetric high the satellites had been whispering about all along. This was the moment everything changed. The criteria started stacking. Elevated bathymetry relative to surrounding oceanic crust. Extensive area, about 4.9 million square kilometers. Distinct geology, silica-rich rocks and metamorphic histories tied to Gondwana. Crustal thickness and low velocities that scream continental. Isolation from Australia with deep oceanic basins in between. One by one, the boxes ticked. In 2017, a group of geologists put it plainly in a peer-reviewed paper. Call it what it is, a continent. Zealandia. But even with the stamp, the story wasn't done. People asked a fair question. Could a large igneous province mimic this? Massive flood basalts can sit thick and high. The counter sat in the petrology and the seismic detail. Large igneous provinces tend to be mafic, magnesium and iron-rich, fast to seismic waves with magnetic striping that tells a volcanic story. Zealandia's patchwork showed felsic dominance, inherited zircons, metamorphic belts, and velocity structures that matched thinned continental crust, not a basaltic pile. And the magnetics? Messy, overprinted, lacking the neat symmetries of young ocean floor. In a core store chilled to protect samples, a scientist slid open a tray and tapped a thin ash layer. Microfossils shifted from shallow water assemblages to deeper water forms across a small distance. Exactly what you'd expect as a shelf drowned. Above, sediments fine out, terrigenous grains, thin, carbonate ooze thickens. That's the diary of a continent's margin slipping under waves, not the life of an abyss born far from land. And tucked between some laminae sat a clue we'll come back to. A micron's thin chemical skin on grains that forms right after the seabed jumps or sinks. A kind of timestamp varnish that remembers the exact moment the interface moved. Meanwhile, farther offshore, a seismic line crossed a step where crustal thickness dropped sharply and velocities jumped. A clean base of continent marker. The team flagged it as the edge. Back in the lab, a detrital zircon dataset from a different margin matched age peaks, known from East Antarctica and Australia's former Gondwanan edges, tying Zealandia's fragments to a family album long scattered by rifting. Impact isn't just academic. Classification controls attention. Continent isn't a vanity plate. It's a budget line, a map layer, a reason to drill, a reason to monitor hazards where a mobile, thin continent rides the boundary between major plates. The more the rock spoke, the more the classification debate faded. The case wasn't marketing. It was mineralogy, physics, and consistent maps. A small moment sealed it for a skeptic. During a seminar, someone flashed a plot. Crustal thickness against P-wave velocity for different provinces. Oceanic fields clustered tight. Large igneous provinces formed another cloud. Zealandia's points, scattered by rifting, still sat squarely with continents. The room went quiet. The skeptic scribbled a note and underlined it twice. So yes, pretty contours drew the ghost. But rocks decided. And they said this. Continental crust where it shouldn't be, thinned and drowned, still carrying the deep-time memory of Gondwana. Which raises a harder question. If a continent can be stretched until it slips below sea level, what did the stretching, and everything that followed, do to the plates around it? To understand how you lose land without an impact, we need to watch the slow drowning. The slow drowning, rifting, thinning, and a vanished land. To see Zealandia disappear, first see it whole. It sat welded to Gondwana's southern rim, tied to East Antarctica and Eastern Australia. Forest, rivers, reptiles, the works. Around the late Cretaceous, roughly 83 to 79 million years ago, the supercontinent began to unbuckle. Heat pooled in the lithosphere, magma threaded weaknesses. The crust domed and cracked. Rifts opened like zipper teeth. Not all at once, but step by step across millions of years. The early tiers were tentative, half-grabens forming inland lakes and fault-scarped valleys. Then the system committed. As Zealandia pulled away from Australia, the crust stretched like pizza dough. Thinner, weaker, lower. Here's the rule that decides a continent's fate. Thick continental crust floats high because it's buoyant. Thin it by 30, 40, 50% and isostasy takes over. The keel lifts out of the mantle, the surface drops. The rocks didn't sink because they were heavy. They sank because the support column shrank. As the rift matured, hot asthenosphere rose beneath new basins, fire met water, and volcanic margins flared. But heat doesn't last. The newborn plate cooled, became denser, and the whole region subsided. Land that once sat as hills became coastal plain, then estuary, then
shelf drowned by a shallow, warm sea. Meanwhile, plate boundaries were playing musical chairs. Subduction to the north reorganized. The direction of slab pull flipped around parts of the Southwest Pacific. When subduction initiates or retreats, it drags neighboring plates, re-angles stresses, and changes which edges rise and which edges fall. Zealandia got caught between a growing Tasman Sea to its west and evolving trenches to its north and east. The result wasn't a clean break like a cracked plate. It was a mosaic twisting and tilting. Some blocks lifting, others sinking, hinges shifting through time. This was the moment everything changed for the landscape. River systems lost their gradients and began dumping loads onto widening shelves. Coastal swamps marched inland. The fossil ledger agrees. Pollen from land plants and older beds gives way to marine microfossils, foraminifera that prefer shallows. Then deeper water species as the shelf edge moved over the same spot. Dinosaurs and reptiles that roamed linked land vanished from the record, replaced by marine reptiles and fish. The drowning wasn't a single wave, it was a stairway down. Rift, sag, brief still, another drop. Across what's now the New Zealand highlands, old rift shoulders held on as islands. Elsewhere, basins sagged into deep sediment traps. Add in thermal subsidence, cooling over tens of millions of years, and you get a long fade to blue. By the late Cretaceous into the Paleogene, about 94% of Zealandia lay below sea level. The peaks we see today, Araki, the Southern Alps, are late uplift on a mostly submerged stage. While that was happening offshore, a different switch tripped along the plate boundary that would shape the next act. The relative motion between the Pacific and Australian plates changed orientation. Strike-slip shear along the Proto-Alpine Fault started to translate and squeeze the drowned continent's spine. In places, compression thickened the crust, raising islands. In others, extension behind subduction zones opened back-arc basins, deepening the sea. Zealandia didn't just sink. It buckled, rotated, and breathed. A field team pulled a core from a drowned valley off a present-day coast and found wood, actual tree tissue, turned to dark, waterlogged peat, buried beneath marine mud. Radiocarbon pinned it to a window when land stood briefly higher. Above, a storm-born sand sheet sealed it, and over that, shells from species that need deeper, calmer water. The core is small, but the story is big. Pulse subsidence, not a smooth slide. What nobody knew at the time was how political the drowning would become. If maps labeled this region continental, budgets would follow for hazard monitoring and exploration. If it stayed fragmented microcontinents, interest would scatter. But the Earth doesn't care about our categories. As subduction along the Kermadec-Tonga system accelerated rollback in places, Zealandia's northern margins flexed. As the Tasman Sea stopped spreading, thermal sag finished the job in the west. Every adjustment altered coastlines, currents, and the sediment clock that fuels future resources and future risk. In the aftermath of rifting and cooling, a quiet consequence set in. Isostatic equilibrium with a twist. Load the thinning crust with sediments from eroding highs, and it sags more. Strip those highs later through uplift and rivers, and the lows keep sinking under the added weight. That's how you end with shallow shelves draped in thick sediment and deep basins adjacent. Classic continental margin anatomy, just mostly underwater. So how do you lose a continent without an asteroid? You heat it from below, pull it apart, let it cool, and rearrange the forces at its edges until buoyancy can't keep most of it up. Zealandia didn't fail in a catastrophe. It failed in increments, guided by physics, which sets up the next tension we have to face. Once a continent is thinned and mobile along an active boundary, it doesn't stop moving. And that means hazard, uplift, and the rumors of re-emergence aren't a myth. They're the next chapter we're already living. Hidden in plain sight, politics, semantics, and funding. Here's where the science met the filing cabinet. Labels aren't just words, they open doors. Call it a continent, and suddenly you're talking national strategies, exploration budgets, curriculum rewrites, and hazard monitoring. Call it a collection of fragments, and it's another niche project no one has to fund at scale. The rocks were clear, the institutions weren't. Definitions got slippery. Geologists meant continent as a crustal category. Thick, buoyant, silica-rich, coherent, and large. Policymakers heard new land and pictured flags on beaches. Textbook authors ask how you draw a mostly underwater continent on a world map for kids. Cartographers wanted a boundary they could print. Meanwhile, every committee had a different threshold for what counts, and who gets to say so. This was the moment.
Everything changed for the people chasing grants. A team submitted a proposal using Zealandia continent in the title. A reviewer wrote, "Overstated, avoid hype." The team toned down the language, got the money to collect the data, then watched the top journal run a cover story 2 years later calling Zealandia exactly what they'd said it was. Same rocks, new permission. While that was happening in meeting rooms, budgets moved in the background. Continent status meant you could justify coordinated mapping, bathymetry, seismics, gravity, and GPS built into a single program rather than scattered cruises. It meant governments could invest in hazard models that treat a mobile continent as one system, not a patchwork of islands. It also meant industry started circling. The phrase critical minerals has a way of speeding up calendars. Resource implications sharpen the edges. Along Zealandia's margins sit cobalt-rich crusts, rare earth elements, gas hydrates, and seafloor sulfides near volcanic ridges and back-arc basins. Exploration companies don't need beachfront. They need legal certainty. But the map doesn't care about exclusive economic zones. The crust does. If Zealandia is a continent, the narrative shifts from scattered prospects to a unified, evolving margin with shared risks and cumulative impacts. That's attractive to planners and alarming to ecologists. Public perception didn't help. Say lost continent, and half your audience hears Atlantis. Say eighth continent, and the other half thinks you invented one to sell t-shirts. Communicators had to thread the needle. Not a myth, not a marketing gimmick. A real continent by geological criteria that happens to be 94% underwater. The misframing slowed textbooks and muddied policy briefings. Students asked why their maps showed 7. Teachers shrugged and moved on. Meanwhile, everything else was accelerating. International seabed rules were evolving. Countries renewed claims, data portals filled with beautiful maps that still labeled Zealandia as continental fragments. At the same time, hazard agencies faced a practical question. Do we plan for a continent-scale system that transmits stress along its spine, or keep drawing island-by-island risk boxes? Insurance firms started reading the papers. Premium models don't wait for textbook consensus. Unknown to most of the public, an unglamorous step made a difference. Standardizing criteria in accessible language. Scientists distilled the checkboxes: area, elevation relative to abyssal plains, crustal thickness, seismic velocities, distinct geology, and isolation by deep oceanic basins, and published them with curated figures. It wasn't flashy, but it gave editors, civil servants, and teachers something to copy without getting yelled at in peer review. Slowly, map services added outlines. Museums updated wall graphics. Newsrooms stopped using Atlantis B-roll. A micro story from the trenches. A young researcher mailed a manuscript to a journal with Zealandia, the continent, in the first line. It came back with a polite no. 18 months later, the same journal asked for a commentary. Could you explain Zealandia's continent status for our readers? The researcher laughed, wrote the piece, and included a paragraph on why semantics shape budgets. It became the most downloaded article of their year. There was one more layer: equity in naming and stewardship. In Aotearoa, New Zealand, the Maori name Te Riu-a-Māui situates the continent in a living landscape, not just a data set. That matters when you're balancing exploration, conservation, and cultural values over a place that's both ancient crust and present home. A continent isn't just a classification, it's a jurisdiction of attention. Classification drama aside, Zealandia still moves. And movement is the one thing budgets can't ignore. Because if a thinned, restless continent is riding an active boundary, update the map someday becomes update the hazard plan now. And that's where the Alpine Fault and the Ring of Fire step in. The plate that won't sit still. Alpine Fault and the Ring of Fire. While committees argued over names, the ground kept talking. Zealandia sits astride one of Earth's sharpest boundaries, the Australian Plate,
sliding past and into the Pacific diving beneath and shearing alongside. The Alpine Fault is the stitched seam, nearly 600 kilometers of right lateral strike slip with a twist of compression that shoves the Southern Alps up at rates you can see in a human lifetime. It's been locked for decades, maybe longer. Locked faults don't feel safe, they store energy. The last major Alpine Fault rupture was around 1717. With a typical recurrence interval of roughly 300 to 400 years, we're now about 307 years into that cycle. Here's why this seam matters. When the Alpine Fault breaks, it usually does so in big steps, magnitude 7.5 to 8+ ruptures that run hundreds of kilometers. Paleoseismic trenches along river terraces show a pattern. Clusters of large events, then long, quiet periods. The last major rupture around 1717 ripped hundreds of kilometers and shifted the ground meters sideways. Since then, strain has been loading again. Meanwhile, the shear doesn't just split the South Island, it drags Zealandia's spine, rotating blocks, bending basins, and twisting stress into neighboring faults. Unknown to most people, subduction lines these edges like tripwires. Northward, the Hikurangi margin near the North Island transitions to the Kermadec and Tonga trenches, some of the fastest subduction on Earth. There, the Pacific Plate dives steeply, and back arc basins like Havre open behind the arc. Southward, the Peisker region marks a mirror image, subduction dipping beneath the South Island southwest. Zealandia sits between these jaws, strike slip in the middle, subduction at both ends, and extension in the back arcs. It's a tectonic vise that squeezes, stretches, and spins. This was the moment everything changed for hazard models. GPS stations anchored across the islands and offshore platforms began mapping motion in millimeters per year. Sideways creep along the Alpine Fault corridor, uplift in the Alps, subsidence around some coastal plains, and slow rotation of crustal blocks. After the 2010 to 2011 Canterbury earthquake sequence near Christchurch, instruments showed permanent shifts. The crust didn't bounce back. Families rebuilt while the land kept inching. Insurance adjusters learned a new language: post-seismic relaxation, afterslip, time-dependent hazard. While that was happening on land, offshore coupling waxed and waned. The Hikurangi margin hosts both locked patches, capable of big quakes, and areas prone to slow slip events that release strain silently over weeks. Slow slip doesn't shake your house, but it can transfer stress to locked segments and change when they fail. Volcanoes in the Taupo volcanic zone answer to that tug-of-war. Fluids rise, magma batches, and the back arc breathes heat. To the north, the Kermadec Arc's submarine volcanoes remind us that most eruptions here never breach air, but their plumbing is part of the same circuit that loads faults. Get this, Zealandia's edges don't politely isolate their hazards. Stress rolls through the crust like a tide you can't see, guided by old fabrics cut into the drowned continent. A rupture on one segment can nudge another toward failure. A slow slip patch can relax one edge while tightening another. In 2016, the Kaikoura earthquake thread ripped more than a dozen faults in a complex cascade, rearranging stress across a region in minutes. That strike slip, thrust, and oblique motion teaming up, exactly the kind of choreography you expect where a thin continent rides an active boundary. Meanwhile, south of Fiordland, the Pulsegur subduction margin dips beneath Zealandia's southwestern flank. Gravity and seismic imaging trace a slab curving down. Bathymetric scarps mark trenches and accretionary wedges. Up north, the Hikurangi forearc sometimes pops with tsunami earthquakes, events that don't shake hard locally but displace the seafloor efficiently. Hazard maps have to blend all this: Alpine fault, strike slip shocks, coastal uplift or drop, offshore subduction tsunamis, liquefaction in lowlands, and volcanic ash when the back arc gets lively. It's not one hazard, it's a network. Micro story. A couple in Christchurch checks the GPS graph from a nearby station on a community website. The line has a kink, 2011, then a new slope. It's subtle, millimeter per year, but it's steady. They decide to rebuild on stronger foundations, higher on their section. Months later, a moderate quake rattles dishes. The GPS line barely twitches because the creep continues regardless. What nobody knew at the time was how mantle flow beneath Zealandia modulates this dance. Subduction to the north and south drags slabs. Rollback can pull arcs away, opening basins and changing stress direction. Tomography hints at torn, contorted slabs under the Southwest Pacific. When a slab segment peels back, it can accelerate trench retreat, promote back arc spreading, and load strike slip sections differently. That translates upstairs to whether coastlines rise or sink over decades, whether rivers steepen or meander, and which faults inch toward their next break. In the aftermath of each major event, planners face the same question. Did the clock reset, or are we in a cluster? Paleoseismic records along the Alpine Fault suggest supercycles, periods when several large ruptures happen within a few centuries, separated by longer lulls. If we're entering an active window, the near future will feel busier. Preparedness windows and code cycles have to assume that possibility, not chase it after the fact. Here's the quiet consequence. A mobile, thinned continent at a plate junction doesn't grant stable baselines. Uplift and subsidence redraw shore risk. Strike slip translates whole valleys. Subduction toggles between quiet and sudden, and slow slip moves the goalpost without a sound. Zealandia won't sit still because the system feeding it won't. And the rumor of re-emergence at its edges. That's not folklore, it's the next clue we need to follow. The re-emergence clues: uplift, seamounts, and drowned shores. Movement is one thing, breathing is another. Around Zealandia's margins, the coastline keeps leaving breadcrumbs. Flat stair steps etched into cliffs, ancient beaches stranded high above the surf, and river mouths that suddenly don't fit their valleys. Uplifted marine terraces line parts of the South Island, clean as ruler marks. Each terrace is a pause in sea level or a shove from below. Stack them, date them, and you get a pulse record of how the crust lifts in bursts, not drifts. Here's why those shells matter. A marine terrace forms at the waterline. Waves cut a platform, corals or shells colonize it, and then something changes. If the land jumps during a quake, that platform pops up into the salt spray zone and stops growing. Radiocarbon dating shells or coralline algae pins the moment. Along the Kaikoura coast, terraces step up like bleachers, some lifted meters in single events. Inland, river profiles kink, where channels adjusted to sudden elevation gains. This isn't slow isostasy alone, it's tectonic breath holding, then exhaling hard. Meanwhile, drowned landscapes tell the counterstory. Offshore multi-beam sonar maps reveal river valleys now flooded, and fjords that once extended farther. Divers find tree stumps rooted in place below the waves, forests that grew when the ground stood higher. Lift a stump and its rings stop on a date. The mud above holds marine microfossils that don't belong in a forest. It's a tidy sequence: soil, wood, storm sand, then shells from deeper, quieter water. Subsidence took over, but not forever. While that's happening inshore, the seafloor to the north bristles with seamounts, volcanic cones scattered along the Kermadec arc and back arc. Most never break the surface, but some have in the past, only to sink again. Uplift and volcanism aren't the same thing, but they're cousins in this neighborhood, both answering to how the plate bends, how the slab rolls back, and how the mantle feeds heat into thin crust. In places you can see drowned coral caps on seamounts, flat-top guyots that once hosted reefs near sea level before the seafloor sagged. Get this, shorelines carry scratch marks you can read like a tide chart for centuries. Notches in sea caves, benches carved by bio-eroding organisms, barnacle bands now perched above spray. Tie those to tide gauge records and GPS, and you see the mismatch that matters. Global sea level rising one way, local land moving another. A harbor that seems to be swallowing wharves may be sinking faster than the ocean's rising. Another headland, battered by higher waves, might be climbing even as sea level creeps up. Fisheries feel it when currents shift around a reborn terrace. Ports feel it when seabed siltation changes because a river's base level jumped. Microstory. A diver working a kelp survey brushes a smooth, horizontal rock ledge at 10 meters depth and feels grooves. Later, in the lab, radiocarbon dates from a thin algal crust on that ledge cluster around the same century as a known uplift pulse on land. The ledge was once a living shoreline. The kelp forest is growing on yesterday's beach. Meanwhile, storm archives are changing. A low, drowned shelf used to break waves early. A lifted terrace focuses energy back toward a different cove. Erosion hotspots migrate without a new subdivision or a seawall to blame. Beach profiles adjust, sandbars reroute, and what looked like a stable dune line eats itself after a year of unusual winds because the underpinning terrace stepped. Surfcasters swear the rip moved. The LiDAR says the platform did. Seamount chains add another clue. A conveyor of creation and sinking tied to plate motion. As the Pacific plate slides, a stationary mantle plume can build a volcanic swell.
As the crust cools and moves off, it subsides. On the back arc side, spreading can lift and lower in fits, creating new seamounts and burying old ones in sediment. Dredged samples from some of these peaks carry shallow water fossils far below present sea level, a breadcrumb trail for former sea surfaces dragged down by flexure and load. Here's the twist that keeps planners up. Some uplift is elastic, snap up in a quake, then a slow glide downward as the crust relaxes. Some is permanent, crustal thickening that sticks. GPS catches the slow parts, terraces archive the fast parts, put them together, and you can spot neighborhoods that will creep out of flood risk over decades, and others that will sink into it despite seawalls. A living atlas needs both: tide gauges for water, monuments for land, and cores for the memory of what happened when we weren't measuring. While that was happening along the coasts, offshore sediment drapes thinned unexpectedly over newly high blocks, altering currents that steer larvae and nutrients. Fishers noticed a shift in catch species. Oceanographers watched eddies detach differently around headlands that barely changed in elevation but crossed a threshold in shape. Shipping routes took a second look at approach channels after a moderate quake. No visible landslide, but silt resorted by changing wave energy on a subtly lifted platform. This is the quiet consequence. Re-emergence isn't a myth of lost kingdoms rising. It's centimeters to meters in the right places at the wrong times. It's a wharf built for last century's mean sea level on ground that's been sinking a millimeter a year since your grandfather poured the concrete. Zealandia breathes along its edges, and that breath turns into currents, storms, and livelihoods. It's a bluff that shrugs upward in one night and changes a bay's resonance. If it breathes, it stores memory, and that memory is trapped in layers below the waves, waiting for a drill bit and a microscope to read the clock. Drilling the memory, cores, microfossils, and a climate time machine. If shorelines are scribbles in the margin, cores are the book. To read Zealandia's breath, scientists sailed out with a plan simple in concept and brutal in execution. Drop a pipe into moving water, bite into mud and rock, and lift a pencil-thin column of time to the deck without smearing the pages. The International Ocean Discovery Program targeted saddles and basins along Zealandia's margins, places where sediments fell like snow, grain by grain, year after year. The gamble, buried within were microfossils small enough to fit on a pinhead and precise enough to time tectonic pulses. And sometimes, right where the seabed stepped, an ultra-thin chemical veneer formed, a mineral skin that locks in the moment the interface changed. We'll come back to that. Here's why that matters. Foraminifera, tiny shell protists, build their homes from seawater chemistry. The oxygen isotopes in those shells track temperature and global ice volume. Carbon isotopes, echo circulation, and carbon cycling. Pollen grains blow from land and settle offshore, a drift of terrestrial life that thickens when rivers run close and thins when shorelines step back. Stack these signals and you get a heartbeat. Warm versus cool, shallow versus deep, close land versus far sea. Layer ages with magnetostratigraphy, flips in Earth's magnetic field recorded as iron minerals align, and the pages fall into order. Aboard one expedition, a core came up glossy and green-gray, banded with faint laminae. Under a microscope, the first centimeters held coastal-dwelling forames, chunky and tolerant of turbidity. Deeper down, delicate deep-water species dominated, the kind that prefer quieter, colder settings. Between them, a razor-thin ash layer from a known eruption pinned the date. An onboard paleontologist leaned back and said, what the graph already implied. The shelf drowned here, fast enough that ecology flipped inside a few thousand years. Meanwhile, another site far to the north told a different rhythm. There, pollen spikes punctuated marine mud, bursts of land plants that made no sense unless shorelines advanced toward the drill site, rivers freshened nearby waters, or wind fields changed to carry more dust. The team cross-checked with grain size, coarser sand pulses aligned with pollen peaks, classic signatures of a shoreline stepping seaward during uplift or lowered relative sea level. The cores didn't resolve single earthquakes, but they sketched the stair steps we'd seen in terraces, now preserved offshore with dates to match. In the same layers, a whisper-thin ferromanganese coating hinted at an immediate chemical reset when the water depth changed, a tiny timestamp we'll use later. This was the moment everything changed for climate context. Isotopes stitched Zealandia's motions to global events. Around 34 million years ago, oxygen isotopes jumped the Eocene-Oligocene transition,
the birth of a large Antarctic ice sheet. In
Northern Zealandia, sediments shifted from carbonate-rich shallows to deeper siliceous ooze within that steppe, matching an uplift to the north and subsidence to the south as subduction initiated and arcs reorganized. A regional tectonic shove appeared in the same chapter as a global climate pivot. While that was happening in isotope graphs, tiny fossils mapped currents. Planktonic foram assemblages swapped species that ride warm subtropical waters for those preferring cooler subantarctic flows. That flip told oceanographers when gateways opened or closed how ridges and sills sculpted the Tasman circulation, and how Zealandia's sinking and tilting tweaked the conveyor belts that feed nutrients and regulate heat. Cores from east of New Zealand showed pulses of diatom-rich layers, blooms triggered by upwelling, stacked against intervals of carbonate dominance. The alternation mirrored changes in wind fields and plate-driven topography that steered westerlies and the subtropical front. Microstory. In the core lab, a scientist brushed a smear on a slide and froze. Among usual marine tests sat a cluster of odd pollen with thick walls and spiky ornamentation. Gymnosperm types, typical of upland conifers. They weren't supposed to be there in that quantity, not 80 kilometers offshore. A few trays later, a thin peat fleck appeared, barely a millimeter across, but unmistakably terrestrial. The count spiked across just a couple of centimeters. The interpretation: a transient low stand or local uplift pushed a river mouth seaward. A storm rafted forest mats out. The shelf edge moved past the drill site and then retreated again. A land bridge? No. A land reach. Brief, enough to change what fell from the air and rivers. What nobody knew at the time was how much gas hydrates would complicate the story. In deeper basins, cores cut through layers where methane ice cements pore spaces. As temperatures and pressures shift with burial, hydrates form and dissolve, altering sediment shape. Geochemists read sulfate methane transition depths as a second clock, tracking fluid flow that waxes when tectonics squeeze and wanes when basins relax. Those same layers tied directly to hazard and resource debates. Hydrate stability fields move when the seafloor heaves or subsides, changing slope stability and the odds of submarine landslides that can fire off local tsunamis. Meanwhile, tephra, the ash fingerprints of explosive eruptions, stitched a precise scaffold through chaos. Each shard's chemistry matched the volcanic source on land. A topoblast here, an earlier arc eruption there, all falling across the sea and pinning time slices across multiple sites. With that lattice, modelers could align uplift pulses on one margin with subsidence on another and ask the hard question: are these in phase because of far-field sea level or anti-phase because of local tectonics? The answer kept coming back mixed. Global water plus local motion superimposed. In the aftermath of months at sea, the cores moved to cold rooms. Their stable isotope lines smoothed into curves, magnetic flips confirmed ages, and microfossil counts became bars and colors. The composite showed cycles, rift sag and thermal subsidence, punctuated by uplift tied to boundary reorganization. Warm currents intruding, then retreating, ice volume rising, then falling. It wasn't a single drumbeat. It was polyrhythm, tectonics and climate improvising over the same bars. Here's the quiet consequence. Cores turned Zealandia from a shape on a gravity map into a metronome you can date. They taught planners that terrace steps aren't local quirks. They're part of system-wide beats. They taught climate scientists that ocean gateways in the Southwest Pacific matter for global heat and carbon. And they taught everyone else that a drowned continent keeps a diary, written in mud, shells, ash, and chemistry, of every breath it's taken. The next clue sat deeper still, in forces beneath the crust that sometimes rewrote the rhythm without touching sea level at all. The overlooked signal, gravity, heat flow, and mantle anomalies. We've been reading the crust like a ledger. Now we had to meet the puppeteer. Gravity maps, those sea surface wiggles turned into mass portraits, started showing patterns that didn't fit tidy rift and sag stories. Broad positive belts meant denser material below. Long negative swaths hinted at thicker, buoyant roots. Across Zealandia, the quilt wasn't uniform. Some margins carried unexpected lows, as if the crust were puffed up from beneath. Others showed highs where you'd expect cool, dense lithosphere. The message was simple and annoying. The mantle was adding its own verses to the song. Here's why gravity matters here. Strip away the predictable pieces. Topography, sediment loads, water depth,
and the residuals point at density anomalies in the lithosphere and upper mantle. Along northern Zealandia, residual gravity lows lined up with spots of anomalously shallow bathymetry and slower
Seismic velocities, the sort you see above warmer, weaker mantle. South and west, belts of higher gravity paired with deeper basins and faster velocities. Cooler, stronger plate. That patchwork correlates with where uplift pulses stack terraces versus where drowned valleys keep deepening. The crust isn't just moving, it's being helped or hindered from below. Meanwhile, heat flow measurements started to whisper the same thing. Drill holes and seafloor probes recorded upward heat leaking faster in arcs and back arc basins, slower across older, thicker blocks. In northern Zealandia, heat flow ran higher than a simple cooling plate model predicted. That extra warmth weakens the lithosphere, lowers its effective elastic thickness, and makes it more likely to flex and warp with regional stress. A study mapping effective elastic thickness across Zealandia showed broad swaths of low values, especially in the north, thin, thermally softened lid, contrasted with stiffer zones to the south and along older cratonic crumbs. Translation: some parts of this continent bend like cardboard, others behave like plywood. If the crust is the car's suspension, the north has soft springs and more bounce. The south rides on stiffer shocks. Or think of it like bread in an oven. A warm, thin crust domes and sags easily, while a thicker, well-baked crust holds shape. Same heat from below, different reactions at the surface. This was the moment everything changed for our tidy subsidence curves. If mantle flow patterns feed heat into thin crust, the same sea level rise can drown one margin while another holds its head up. Gravity lows plus elevated heat flow predict buoyant uplift in places without an obvious surface load change. That's how you get stranded beaches where no big earthquake is on the books, and continued subsidence in deltas even during quiet tectonic years. The overlooked signal wasn't small, it was foundational. While that was happening in the data, seismic tomography offered a blurry window into the engine room. Under the Kermadec Tonga sector, fast anomalies pierced deep, cold slabs sinking. To the south and west, slower corridors suggested warmer upwelling or stagnant hydrated mantle. Beneath Zealandia's northern margin, an irregular, low-velocity zone arced inland, consistent with the retreating slab suction, bringing hotter asthenosphere closer to the base of the crust. Suction sounds esoteric, but it's practical. Trench rollback can pull mantle toward the trench, thinning and heating the overriding plate, priming it for uplift, extension, or both. Unknown to them, across town, a modeler toggled one number mantle viscosity inside a regional flow simulation. With a slightly weaker mantle wedge beneath northern Zealandia, the output flipped from a calm, decaying subsidence to a wobbly, quasi-periodic flex. Decades-long uplift pulses interleave with subsidence, out of phase with pure, eustatic sea level cycles. The model painted terraces and drowned stumps in the right places without changing earthquake timing. It also pushed slow slip zones into and out of favor as coupling shifted with temperature. One variable, a different coastline. It's like loosening a guitar string a quarter turn. The same fingers, faults play, but the song shifts key because the tension changed. Get this, gravity also caught hidden loads moving around. After big quakes, water redistributes, sediment pours off scarps, and the elastic plate responds. Satellite gravity missions sense tiny changes in mass near certain margins post-event. Pair those with tide gauges and GPS, and you can separate ocean water rise from ground drop. In several harbors, the sea level rise that terrified locals was mostly land sinking over warm, weak lithosphere being flexed by regional stress. That doesn't make it less real. It makes it more solvable. Rebuild higher, not just taller seawalls. Meanwhile, effective elastic thickness maps explain why some slopes fail in quiet weather. Low stiffness means small stress changes tip the balance. A hydrate-charged slope perched above a warm wedge is a landslide waiting for a spring storm. That's tsunami planning driven by heat, not just faults. Insurance quietly started ingesting those maps. Here's the quiet consequence. Mantle anomalies can refloat or drown the same coastline on human timescales, independent of global sea level. Gravity, heat flow, and tomography aren't background. They're the metronome beneath the metronome. Ignore them, and your hazard timelines slip. Factor them in, and once a century floods become twice a decade in one bay, while a neighboring headland rises out of trouble.
If the Mantle's the puppeteer, earthquakes are the strings snapping. The show is the uplift and subsidence we live with day to day. Quake roulette, recurrence, supercycles, and stress transfers. Long quiet isn't comfort, it's the setup. Along the Alpine Fault, the diary in the dirt says big ruptures don't arrive evenly spaced. They cluster. Paleoseismic trenches cut into river terraces show sharp, sandy earthquake layers stacked like footnotes to chaos. Each one tied to sudden offset, each separated by centuries that sometimes shrink. When researchers dated buried soils and toppled forest horizons, a pattern emerged. Several major events in a few hundred years, then a longer lull. The last great break in 1717 was one of those punctuation marks. Since then, strain's been storing. Here's why clusters matter. If faults share load through a crust laced with old Zealandia fabrics, one rupture can tip another toward failure. Think of it as a crowded table. Nudge one plate and the cutlery rattles 3 seats away. Coulomb's stress transfer quantifies that nudge. Positive changes load a neighbor. Negative changes buy time. After the 2010 to 2011 Canterbury sequence, models showed lobes of increased stress arcing toward other faults. Then 2016's Kaikoura event stitched a dozen-plus faults in a ragged cascade, rearranging stress yet again. None of those were the Alpine Fault, but they didn't need to be. They pushed and pulled the system it lives in. Meanwhile, offshore, subduction coupling sets the tempo at the margins. The Haikurangi interface has patches that lock tight and patches that creep in slow slip events. Weeks-long silent releases that barely jiggle chandeliers but shift stress meters. When a slow slip pulse unzips down dip, it can load the locked shallows or ease them depending on geometry. Pair that with slab rollback tugging on northern Zealandia's base and you've got a moving target, coupling waxes, wanes, and migrates. Volcanic plumbing in the back arc answers to those shifts too. Fluids rise, pressure changes, and eruption probabilities wobble without a single felt quake. This was the moment everything changed for recurrence models. The simple, every X years clock gave way to supercycle thinking. A long build punctuated by clusters of large ruptures that reorganized the whole stress field. Along the Alpine Fault, trench records suggest sequences where 3 or 4 magnitude 8 events stack within centuries, separated by quieter millennia. If we're in the back half of a long quiet, the next century could be active. That doesn't guarantee a date. It says the dice are loaded. While that was happening on paper, GPS was writing the present. Velocities along the fault show millimeters per year of shear, piling up, with vertical components that match uplift in the Alps and subsidence in forelands. After shocks, station step, then creep, afterslip and viscoelastic relaxation bleeding strain into nearby zones. Some coastal gauges saw sea level rise that was land drop. Others recorded calm despite global rise because the ground lifted a little after an event. That's Quake Roulette's quiet side effect. Relative sea level is hazard math plus tectonic bookkeeping. Unknown to them across town, a hazard team ran a time-dependent forecast that blended paleoseismic intervals, present coupling from offshore seismic reflection, and slow slip catalogs. The map that came out didn't blink red everywhere. It flashed likelihood increases along corridors where stress had been added and coupling stayed high. It also downgraded a few places where slow slip had recently bled strain. The headline wasn't apocalypse. It was a call sheet. Here are the segments watching the same clock. Get this. Volcanoes play a supporting role, not as dominoes that topple faults, but as gauges of the system's pressure. In the Taupo zone, subtle changes in magma reservoir behavior have aligned with slow slip pulses offshore. Deformation at calderas has breathed in step with plate interface shifts. That doesn't mean the next quake triggers an eruption. It means the same forces nudge both in different languages. Micro story. A school on the South Island runs an earthquake drill every term. Kids file under desks, then out to the field, bored. A few months later, a moderate shock rolls through at dawn. No injuries, just rattled nerves and a crack in the hall. In the local council office, a planner pulls up a dashboard. GPS lines kinked slightly, coupling maps updated, slow slip detected offshore last week. The drill feels less routine. The evacuation route gets a tweak. Not because panic is fashionable, but because the system just whispered. Here's the quiet consequence. Recurrence in a mobile continent isn't a metronome. It's a band playing in supercycles. Stress transfers mean one player can shift the beat for the rest. Preparedness can't wait for perfect foresight. It has to treat likely within a human lifetime. As actionable and clusters happen, as code design, insurance modeling, and emergency planning. That's not doom, it's alignment, building in the direction the ground is already moving. In the aftermath of the next major alpine rupture, aftershocks will spray, rivers will jump, terraces will lift, some coasts will drop, and offshore slow slip will adjust the edges. The dice will roll again, and the table will shift. Roulette isn't random when the wheel is tilted. Roulette isn't random when the wheel is tilted. The tilt is strain history, coupling, and the Mantle's slow shove beneath Zealandia. The prize and the price. Minerals, metals, and marine frontiers. Follow the money, and you find the next fault line. As Zealandia's outline sharpened, a different map lit up. One traced by cobalt-rich crusts on seamounts, rare earth elements in nodules and phosphorites, gas hydrates in cold, silent drifts, and copper-zinc-gold sulfides piled around black smokers on back-arc ridges. It isn't folklore, it's geology with a balance sheet. Phones, batteries, wind turbines. Our whole electrification push leans on metals that the land is struggling to supply. The ocean, and Zealandia's margins in particular, hold lures that are hard to ignore. Here's what's at stake. Cobalt and nickel crusts accumulate like slow armor on seamount flanks bathed in oxygenated water. They grow millimeters per million years, loaded with platinum, tellurium, and other critical elements. On ridge crests and in back-arc basins, seafloor massive sulfides form where hot, metal-rich fluids hit cold seawater, dropping chalcopyrite and sphalerite in chimneys that later collapse into mounds. Farther afield, gas hydrates, methane trapped in ice lattices, lace continental slopes, and across some plateaus, phosphorite layers and nodules hoard rare earths. Zealandia's geology didn't just drown, it set the table. Action moved quickly once continent stopped sounding like myth. National agencies expanded exclusive economic zone surveys. Multi-beam mosaics and AUV transects filled gaps. Contractors filed exploration licenses on prospective crusts and sulfide fields where law allowed. A research vessel filmed a cobalt-crusted seamount face. Dark, metallic rinds draped over ancient lava, with glass sponges and corals growing like delicate chandeliers from the metal skin. The camera lingered on a squat lobster perched under a ledge. It wasn't a gold rush, it was a moral puzzle with coordinates. Meanwhile, engineers sketched collectors, tracked vehicles to scrape crusts, riser pipes to pump slurry to ships, separation plants on deck. Environmental scientists sketched plumes, fine particles lofted into currents, settling who knows where on filter feeding communities. In sulfide fields, vents host specialized life that feeds on chemical energy. Strip the chimneys and you strip the habitat. Hydrate slopes add another complication. Destabilize the shallowest lattice with warming or physical disturbance, and you can trigger slope failure. In a low-stiffness lithosphere, that's not just a scar, it's a tsunami generator. This was the moment everything changed for policy. The International Seabed Authority debated mining codes for areas beyond national jurisdiction, while countries eyed their EEZs with a mix of pride and caution. New Zealand's conversation pulled in iwi and hapu leaders, fishers, conservationists, and industry. The term Riu-a-Māui showed up on meeting agendas next to critical minerals. The question wasn't whether metals exist, it was whether taking them made sense at all and on what terms. Action on deck got personal. On one survey, a junior engineer watched a live feed as a camera panned across a sulfide mound rimmed with white bacterial mats and fluttering worms. After shift, a recruiter emailed, "Good salary deep-sea mining startup." The engineer stared at the screensaver of a glass sponge lit by the ROV's lights and closed the offer. In their notebook, they wrote, "We can't treat a living archive like overburden. Impact rippled beyond ethics. Fishing grounds sit where currents and seafloor shape concentrate life, often along the same ridges and banks that hoard metals. Port economies rely on predictable siltation patterns. Plumes could modify those. Legal gray zones matter too. Where a seamount straddles an EEZ edge, enforcement and liability get sticky. And the science isn't neutral. Mapping for hazard also reveals resources. Public trust depends on clear walls between safety data and extraction prospecting. Meanwhile, companies pitched light touch tech, precision cutting, low turbidity collectors, staged pilots. Ecologists countered with recovery timelines in centuries, not years. Cobalt crusts grow painfully slowly. Scrape once, and that geologic surface is gone for human timescales. Even with cautious methods, noise, light, and carbon footprints add up. Gas hydrates tempted as bridge fuels with lower CO2 per unit energy, but methane leaks erase that advantage quickly. In a warming world, cracking open a subsea methane bank near weak slopes is the kind of own goal planners dread. Get this, Zealandia's breathing complicates everything. Uplift can reroute currents,
changing larval highways just as a pilot project starts. Subsidence can deepen oxygen, minimum zones that stress seafloor life. Slow slip and quakes can break risers. A region with low effective elastic thickness will flex more under added infrastructure. The resource is real, the platform is restless. Impact isn't only cautionary. The same mapping that scares biologists helps protect. High-resolution habitat maps let governments draw no mining zones around vulnerable vents and coral gardens. Time-lapse monitoring can prove harm or help claims. A pragmatic path emerged in some rooms. Build a precautionary corridor. Science first. Small pilots under strict thresholds, independent monitoring, public data, automatic shutoffs if plumes or noise exceed caps, and a hard stop if recovery falters. It's not romantic, but it's a line in the surf. Unknown to them, across town, a group of students hosted a public forum titled Batteries or Biodiversity. A fisher described a seamount they've worked for decades. A scientist showed a map of cobalt crust thickness and a biohotspot overlay. Same seamount, same flank. The room went quiet, the same quiet as in labs when two datasets line up too neatly. Choices seldom present themselves that cleanly. Here's the quiet consequence. Zealandia holds metals the transition wants, but taking them means touching a living, shifting archive. One that also protects coasts, feeds communities, and teaches us how plates and climate talk. Treat it as a bank account with compound interest, and you'll overdraw. Treat it as capital, natural, cultural, scientific, and you might invest wisely enough to keep options open. Either way, the continent under the waves won't wait. It's moving, with or without us. The Supercycle hypothesis. When plates reorganize overnight. Every so often, the beat stutters. Not just a big quake, not just a new volcano, an edit to the score itself. Geologists call it plate reorganization. Trenches roll back, ridges jump, transforms reroute, and the stress field across whole oceans turns like a school of fish. Overnight is poetic. It's tens of thousands to a few million years. But from a geological perspective, it's a blink. And Zealandia sits right where these blinks land hardest. Here's why that matters. When a subducting slab begins to peel backward, roll back, it drags the trench with it and sucks hot mantle toward the interface. Back arc basins split open behind the arc. Forearcs stretch or crumple. Strike-slip corridors strengthen to accommodate changed relative motions. A ridge jump does the same with different tools. The mid-ocean rift abandons one line and opens another, changing heat flow and buoyancy patterns across nearby crust. For a thinned, floating continent like Zealandia, both moves tug at its edges and torque its spine. Meanwhile, the historical breadcrumbs line up. Cores from northern Zealandia captured a sharp uplift pulse between about 50 and 35 million years ago, meters to kilometers of rise in places, while southern basins deepened. That's the signature you expect when subduction initiates or reorients to the north and rollback accelerates. Suction lifts the overriding plate near the trench. Flexure drops the plate farther inboard. Sediments switch from shallow carbonate to deeper siliceous ooze across that window. Pollen thinned as shorelines sprinted away. The margin didn't just drown, it pivoted. 3 days earlier, if you're living in research time, a tectonic reconstruction stitched South Pacific plate motions through the Paleogene and flagged two moments: a ridge reconfiguration in the Tasman sector and a re-aimed subduction corridor along the Kermadec-Tonga front. Unknown to them, across town, a geodynamic modeler slid those boundary conditions into a flow code. The output showed a baton pass in the stress field. Strike-slip strengthening along the Proto-Alpine corridor, right as rollback to the north, tugged Zealandia's top toward the trench. The Alpine Fault wasn't born, it was promoted. Get this, the same kind of baton pass shows up later in smaller ways. After the Miocene, as back arc spreading pulsed and stopped, terraces stacked on some coasts while drowned forests multiplied on others. That anti-phase behavior is exactly what a reorganized engine does.
push here, sag there, with wavelengths set by lid stiffness. Effective elastic thickness maps, those cardboard versus plywood charts, predict where the pulses land hardest. Northern, warmer lithosphere wobbles more. Southern, cooler blocks resist and store. This was the moment everything changed for the future tense. If reorganizations punctuate the long drift, the question isn't whether Zealandia moves, it's when the choreography changes. Supercycle thinking folds that in plate boundaries load stress slowly. Then a reconfiguration clusters big events. Then the system settles into a new rhythm. In a reorg, basin gateways shift, currents reroute, ash winds realign, and coastlines cross thresholds. We thought we're decades away. Action isn't just in the past record. GPS and offshore coupling maps hint at living asymmetries. Strong, locking patches bracket slow slip, subduction rates differ north to south, and the strike slip corridor is quietly banking millimeters per year. Mantle tomography shows distorted slabs beneath the Southwest Pacific, tears and folds that can catalyze rollback spurts. Those are the ingredients for a minor reorganization, not a static century. Micro story. A geophysicist circles 3 dates on a whiteboard. About 45 million years ago, a mid-Miocene pulse, and now? Then draws arrows from ridge jump and rollback to alpine strengthening, back arc opens close, and coastal uplifts with subsidence flip. The room hums. Someone asks, can this happen on planning timescales? The answer isn't soothing. Parts of it already are. Impact stretches beyond the lab. A ridge jump can lower the heat under one continental corner and raise it under another, changing effective stiffness and flood risk without a single permit filed. A rollback spurt can bias, which slow slip patches light up, altering odds on a locked segment's failure window. Currents that steer larvae and shipping lanes shift when sills rise a few meters. Insurance models anchored to 20th century baselines start lying politely. Here's the quiet consequence. Reorganize overnight means your map's legend dates itself. A living continent in a hinge zone won't honor long-term averages when the mantle rethreads the machine. Treat hazard, fisheries, and infrastructure as if the tempo can jump keys mid-song and you're honest with the ground. Pretend the metronome never stutters and you build for a rhythm that's already changed. The test. Does Zealandia prove Earth is breaking? Okay, time to put numbers on the hunch. We've got a thin continent riding a vice of subduction and strike slip, terraces stepping, drowned forests whispering, cores clocking pulses, gravity and heat flow mapping a soft lid in the north and a stiffer one in the south. The claim is simple. If Earth's entering a high-strain phase, Zealandia should be where the pattern shows first and loudest. Here's the baseline. During normal plate behavior, relative sea level at a coast is global ocean height plus local vertical land motion that averages near zero over long times. Faults creep a little, big quakes reset every few centuries, slow slip comes and goes in patches, and uplift subsidence swings are modest outside major events. Now compare that to the ledger we've built. Centimeter to meter terrace jumps in single ruptures, yes, but also decadal scale vertical drift that flips sign along short stretches. Slow slip migrating down dip and along strike. GPS vectors rotating blocks while subduction rates diverge between north and south. Effective elastic thickness, so low in parts of northern Zealandia that minor stress changes flex coastlines measurably. Action first. We stack the histories. Cores say northern Zealandia rose sharply between roughly 50 and 35 million years ago as subduction initiated and rollback ramped, while southern basins deepened. Later, Miocene pulses rode on back arc breathing. In the present, continuous GPS shows millimeters per year uplift in the Alps, subsidence in forelands, and sideways shear across the Alpine corridor. Tide gauges in some harbors show sea level rise, outpacing global trends. But when you subtract satellite altimetry and barometric effects, the mismatch lands on ground motion, land falling faster than the ocean rises. Offshore, coupling maps bracket locked zones with slow slip corridors. Kaikoura's fault cascade showed the Crust's willingness to play ensemble. Meanwhile, gravity residuals and heat flow outline Mantle help. Warm, weak lithosphere in the north, cool, stronger plate to the south and west. Tomography sketches torn, contorted slabs under the Southwest Pacific, exactly the geometry that fuels rollback spurts and boundary re-aims. Effective elastic thickness maps read like a vulnerability index. Cardboard-friendly north, plywood south. If you wanted a place to test whether the planet's tempo is up, you'd pick a soft-lidded hinge where two subduction jaws and a major strike-slip seam meet. That's Zealandia. Impact isn't just local. We cross-check global signals. Polar motion, the wobble of Earth's spin, has drifted in recent decades as water mass shifts and mantle flow adjust. Some components track ice melt. Some may reflect deep mass redistribution. Sea level fingerprints vary by region. Zealandia's tide gauge patterns fit a zone where vertical land motion dominates variance on decadal scales. Volcanic upticks? The Southwest Pacific Arc is busy by any standard, but what matters is coherence. Slow slip pulses lining up with subtle deformation in the Taupo zone. Ash layers and cores pinning past reorganizations to climate steps. None of that screams unprecedented. It does say currently energized. Microstory. An analyst overlays GPS vertical velocities with a century of tide gauge residuals after stripping global rise and atmospheric pressure. A few ports pop out, residual rise that's mostly land sinking. Another set shows flat sea level because the ground has been creeping up. They plot those against effective elastic thickness. The low stiffness swaths match the biggest mismatches. The punchline isn't a headline grabber, it's a policy lever. Build for ground motion first, water second. So, does Zealandia prove Earth is breaking? Words matter. Breaking implies a new regime of failure beyond plate tectonics. The evidence points to something tighter. A thinned continent at a boundary nexus is entering, or already in, a high-strain interval where multiple processes reinforce each other. Rollback suction softening the lid, stress transfers loading clustered ruptures, slow slip migrating, uplift of subsidence beating against global sea level rise, and resource and hazard stakes climbing because more people and infrastructure sit on the edges.
Here's the nuance. The pulses we see, Eocene uplift, Miocene reorganizations, modern slow slip and complex ruptures, have analogs in the deep record. Zealandia isn't an exception to Earth's rules. It's an amplifier. When the engine down below reads, hinge zones like this broadcast a change as terraces, drowned forests, fault cascades, and shifting currents you can measure in a lifetime. To coastal planners and insurers, that feels like breaking. To a geophysicist, it's the crest of a strain wave moving through a system that never really rests. Meanwhile, the timelines that matter to humans are short. Building codes, port expansions, insurance portfolios, and evacuation routes
live on decades. If decadal scale, vertical land motion, slow slip migration, and stress transfers are all tilting in the same direction along parts of Zealandia, then for practical purposes, the ground is breaking faster than our plans assume. The test result is less a verdict than a warning label. Treat this continent as breathing and assume the breast can deepen without a single headline quake. So the answer lands here. Zealandia doesn't prove Earth is breaking. It demonstrates how a planet that's always in motion concentrates strain and reveals it where the lid is thin and the boundaries are tangled. It's our best early warning screen for a restless phase. If we listen, we get lead time. If we wait for proof to mean catastrophe, we'll say the same thing people always say after the ground moves. We knew, and we were late. Living with a breathing continent. Risk, maps, and mindset. So what do you do when the ground under your house is part metronome, part accordion? You stop treating maps like portraits and start treating them like calendars. A breathing continent needs plans that refresh on a timer, building codes that assume vertical land motion, coastal zoning that budgets for uplift and subsidence, and insurance that prices time, not just hazard type. The rule shifts from build to the last big one to build to the ongoing one. Here's where it lands in real life. If GPS shows your suburb dropping 2 millimeters a year, a century's sea level rise arrives early. That's not a graph, it's a loan term. Raise floor levels now, or accept shorter lifespans and higher premiums. If your headland is creeping up, don't get smug. Cliffs crack when strain changes and terraces pop. Drainage, foundations, and lifelines need slack in the system. Treat every rebuild as a hinge moment. Can this structure ride a few centimeters of step without breaking function? Meanwhile, zoning has to move from lines to bands. Fixed setback distances ignore that shorelines migrate for reasons that aren't just storms. A living atlas, bathymetry, gravity, seismic coupling, GPS, tide gauges, lets councils draw adaptive zones that widen when slow slip clusters or narrow when uplift pulses stick. Permits can carry triggers. If subsidence crosses a threshold or terraces reset in a quake, modifications kick in automatically. It sounds bureaucratic. It's actually mercy, taking the politics out of physics. Early warning isn't just sirens, it's literacy. Slow slip maps should live in local dashboards next to weather forecasts. If coupling tightens offshore, ports can adjust cargo schedules and tugs. If a back arc pulses warming fluids, water managers can plan for ash or altered aquifers. Schools can rehearse not just drop, cover, hold, but post-quake routes that assume bridges may be out in coastal uplift might strand boats. Practice trims panic. Microstory. A coastal town runs a living map night at the library. A geodesist overlays last year's GPS verticals on a big screen. A fisher points at a wharf that's riding low. A retiree asks why her tide calendar feels off. The counselor writes a note. Raise the flood line 3 decimeters on that block. No basements in new builds. And nobody argues because the graph is their street. Insurers have a role if they stop chasing averages. Time-dependent policies can reward retrofits that add base isolation or water-resistant lower stories, and penalize bets on levees where land is sinking. Reinsurance can insist on living atlas compliance. No updated hazard layers, no coverage. That's not punitive, it's alignment. Capital follows clarity. Science funding needs a similar shove. The cheapest safeguard is better measurements. Denser GPS along the coasts and offshore when possible, more tide gauges that share raw data, permanent seismic arrays that can track coupling changes, and repeat multi-beam around key harbors after moderate quakes. Add gravity and heat flow where gaps remain. Those overlooked signals tell ports whether to dredge for silt or lift for land drop. Fund core labs to keep updating the long view. The past calibrates the present. There's a cultural layer too. The Riu-a-Māui isn't just a crustal label. It's a way to center stewardship. Planning with mana, Whenua brings local memory into hazard maps. Places that flooded once in a generation. Dunes that migrated after the last big rupture. Springs that rose and fell with slow slip long before we had satellites. That knowledge isn't quaint. It's high resolution. Get this emergency logistics change on a breathing platform. Stockpiles belong on ground that creeps up or holds steady, not on sinking deltas. Evac routes should anticipate terrace steps that cross road grades. Telecom towers need power redundancy shaped for clusters, not single shocks. After a major alpine rupture, roads will twist. Ports will shoal or lift, and slow slip might quietly reset risk elsewhere. Response plans should pre-authorize surveys, drones for terraces, sonar for
channels within days, so reopened decisions match the new seafloor, not last year's chart. Citizens can help write the atlas. Community GPS on public buildings, shoreline photo posts that repeat frames after storms and quakes, kayak soundings in sheltered bays, and school labs counting microfossils from beach cores after uplift. Small data, big payoffs, especially when it flags a mismatch between global sea level curves and local reality. Here's the mindset shift. Stability isn't the baseline. Update is. Coastlines are moving targets. Risk is a gradient, not a zone, and certainty is rented, not owned. If we build with joints instead of rigid seams, treat maps as living documents, and measure more than we opine, a breathing continent becomes workable. We stop chasing the last disaster and start pacing the present strain. That's not doom, it's craft, learning to live on a stage that moves between scenes. Epilogue reveal, the one detail everyone missed. We planted a loop at the start, one overlooked measurement that flips the ending. It wasn't a headline metric like GPS or a dramatic terrace jump. It was a skin, an ultra-thin veneer of orthogenic minerals, quietly painting Zealandia's drowned surfaces right after each tectonic breath. Here's the setup. In core labs, geochemists strip sediments with weak acids to isolate minerals that form in place. Orthogenic phases like ferromanganese coatings and clay films that precipitate from pore waters within years to decades of burial. These skins record the chemistry of the bottom water and the sediment water interface at the moment they formed. If land pops up or sinks, the interface shifts, pore waters reset, and a fresh chemical varnish grows with a distinct isotopic fingerprint. A graduate student sorting samples for a side project noticed something odd along a core that crossed a known uplift window. In the same centimeter where coastal forames gave way to deeper water species, a razor-thin ferromanganese lamina spiked in cerium anomaly
and neodymium isotopes. Weeks later, on a different margin where subsidence drowned a shelf, another spike. Opposite sign, same coeval ash tide point. The varnish lined up with the terraces on land, but here it nailed the timing to decades, not centuries. Another core, farther west, carried a twin signal tied to a modest slow slip event offshore. Proof that even quiet strain leaves a fingerprint in the skin. Why this matters? We've been dating steps with radiocarbon and magnetics, good but fuzzy on the scale of planning. Orthogenic veneers turn those steps into timestamps. Cerium anomalies track redox shifts when the interface moves. Neodymium links water mass sources as currents reroute over the new depth. Uranium-thorium in the coating pins the age. Stack veneers from multiple sites and you get a continent edge cardiogram with beats you can align across hundreds of kilometers. Action followed fast. A team resampled legacy cores from IODP sites, scraping microns of coating with laser ablation. In one transect off the Kaikoura margin, 3 veneers clustered within a century around a known terrace pulse, each offset slightly along slope, the interface wave racing across the platform after uplift. Northward, along the Haikurangi forearc, veneers paired with slow slip catalogs showed subtle redox flips after weeks-long events, tiny interface breaths we'd never have dated offshore. A parallel lab ran high-resolution scans that caught a manganese-iron couplet, the chemical equivalent of a double heartbeat, matching 2 closely spaced uplift pulses seen on land. Meanwhile, a skeptical reviewer asked if diagenesis changes during burial could smear the signal. Geochemists ran diffusion models and checked element ratios that stay put. The veneers were too sharp, too thin, and too coherent across sites to be overprint. They were event markers, chemical Polaroids. Get this, once you trust the skin, you can revisit the drowning timeline. In northern Zealandia, the classic Eocene uplift we dated to a broad 15 million year window now shows a staircase of veneer pulses stepping through the transition. Not one big shove, but several surges, as rollback wobbled and gateways blinked. That reframes how fast currents reorganized and how quickly ecosystems had to pivot. It also clarifies lead times. In some places, the veneer pulse precedes the biological turnover by years to decades, exactly the window planners can use. Impact lands in 2 places. First, hazard. Veneer clocks let us test whether recent uplift and subsidence pulses have shortened, an early warning for an accelerating strain phase. Second, policy. A veneer-timed atlas can anchor zoning triggers when the interface moves, the rulebook updates. The students' dataset, once a side project, became the keystone others now chase across drowned continents worldwide. Turns out, the thinnest layer was the loudest witness. Zealandia didn't vanish. It breathes, and those breaths, stamped in rock, mud, and a micron's thick.
Mineral Skin, tell us the planet's hinge zones are restless right now. If you want the follow-up where we trace the next likely plate switch across the Pacific and what coastal cities should prepare for, subscribe and watch the companion deep dive queued up next too. It links this breathing continent to the choices waiting on your shoreline.